Here we're going to consider or reconsider some of our circular function definitions. And when I say circular functions, that means I'm talking about my trig functions, sine, cosine, tangent. And we're going to start to reconsider or redefine them, use different terms, but it still means the same thing. So something we mentioned in a previous video, if we start talking about a radian measure theta, we can define that. The radian measure theta can be defined as that distance or arc length divided by r. Now, if the radius is 1, so if the radius of this circle we're considering is 1, then that gives me theta equals s over 1, which essentially just tells me that theta equals s. So thinking about the unit circle, we're always going to have a radius of 1. So I did my very best job drawing by hand this circle in here, considering it of radius 1. So whatever this theta value is, this arc length here, s, is going to be equal to that angle measure as long as we're talking about theta in radians. And this radius, the radius of that circle, is 1. So as I've just stated, this arc length s on the unit circle, meaning radius 1, will be the same as the radian measure of any angle theta. And for each real number s, there corresponds an arc length s on the unit circle. Trig functions with domains which are composed of real numbers are called circular functions. So let's redefine our trig functions using this circular function notation. What we can say here, let me write it this way, we'll say basic circular function definitions. So for any s, any real number s, which is an arc length, so s is a real number and it's an arc length. That s determines a point, all right? So it determines a point, which we can call P, some point xy, on the unit circle. The way we can redefine these, since we're thinking about this point as having an x and a y, and we kind of already talked about this, we'll say that sine of s equals y. Remember, s is that arc length or radian measure. Cosine of s equals x. And tangent of s equals y over x. So this is the same as SOHCAHTOA. We're just now defining that sine represents the y-coordinate, cosine represents the x-coordinate. Why am I not having to say divided by the hypotenuse or divided by the radius? And the reason that is because my hypotenuse or my radius for any triangle, for any triangle I would draw in here, if I draw that down, that radius is going to be 1. So I don't need to write divide by 1 for both of these. Divide by 1, divide by 1. So really it's still SOHCAHTOA. It's just written a little bit differently. And so this is why we're going to use sine equal to the y value and cosine equal to the x value on our unit circle. Similarly, we have the same definitions for our trig functions. Cosecant of s is reciprocal to sine, so that's going to equal 1 over y. Secant of s is reciprocal to cosine, so that's 1 over x. And cotangent s is reciprocal to tangent, so x over y. Again, all these s's, the s is just saying, hey, that angle measure, s is equal to theta. So I can think about putting a theta in there and it would be the same thing. All right. So really just redefining this. If we have some unit circle, beautiful circle, and we've got that theta and radius 1, then we know that this arc length here, which leads to some point, xy. So if we're on the unit circle, we can define all of our trig functions this way. And on the unit circle, this s value is the same as the theta value because it's on a circle of radius 1. So now let's revisit the first quadrant of our unit circle, and we're going to add to it. So if we know all of the values in quadrant 1, then we can reflect them to build the rest of our unit circle. So first things, I'm going to write my degree measures in here. We've got 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And with those degrees, we know we have radian measures. So I've got 0 radian, pi over 6, pi over 4, pi over 3, and pi over 2. And your radian measures, your denominators are going to go 2, 3, 4, 6. 2, 3, 4, 6, and the other one, they'll count down the similar manner. So you'll notice a lot of patterns as you build your unit circle. All right, so now we want to focus on these ordered pairs. Obviously, the quadrantal angles, we're dealing with a circle of radius 1. So up at pi over 2, I have 0, 1, and down here at 0, I have 1, 0. I keep trying to write it wrong. 1, 0. So I'm going to list my other 3 ordered pairs. 1, 2, 3. And the way I do this is I write 1, 2, 3 for my x's, comma, 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 and then I go 3, 2, 1 for my y values. So 1, 2, 3, 3, 2, 1. I divide everything by 2. And then I put square roots over everything in the numerator. Although I don't need to draw square root over 1 because the square root of 1 is 1, right? So we want to remember these ordered pairs, these angle measures in radians and degrees. And so what we said is that if all these points here that we're thinking about, all these points which are labeled, are out at a radius of 1 on this unit circle. Could have been more beautiful, but you guys get the picture. So all of these are on radius 1. Then those points I just listed, that is the exact coordinate if we were to draw that, like, coming in here and drawing a right triangle with a hypotenuse of 1. We would be able to calculate those measures exactly. We also want to remember that cosine is my x value and sine is my y value. So I've got x and y. So the reason this is useful for us is because, well, if I said, hey guys, tell me what sine of pi over 6 is. Here's pi over 6. There's my point. Sine is the y value, so it would be 1/2. Or I could say, tell me cosine of pi over 4. Here's pi over 4. Cosine is root 2 over 2. And we want to be able to take that logic and do that for any value on the unit circle. Let's look at just one more. I could say, well, tell me tangent of pi over 2. Tangent is y over x. 1 over 0, that's an undefined value. So before we practice more using the unit circle, let's continue considering how we build it. So again, in a previous video, we talked about breaking down the unit circle. And I like to think about counting by fourths. So counting by 1/4, as well as counting by sixths. All right, so in quadrant 1, we have our pi over 4. And if I went to list all of these, I would say 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Some of those reduce. I'm really just going to focus on my pi over 4s right now. So we'd have 3 pi over 4. Down here, I get my 5 pi over 4. And in quadrant 4, I get 7 pi over 4. So again, 1 pi over 4, 2/4. 2/4 is just 1/2. 3 pi over 4, 4/4. 1 pi. 5 pi over 4, 6/4. 6/4, so that's 3 pi over 2. 7 pi over 4 and 8/4, which is my 2 pi. All right, well, what we just learned on the last slide is we said that at pi over 4, we're always going to have root 2 over 2. What happens when I take that root 2 over 2 and I reflect it into quadrant 2? Well, you'll notice the x value becomes negative and the y value becomes positive, or remains positive. So I've got negative root 2 over 2 and positive root 2 over 2. Reflecting that down, at 5 pi over 4, both of those would be negative. So I'll get negative root 2 over 2 twice. And then at 7 pi over 4, only the y value would be negative. So I've got root 2 over 2, negative root 2 over 2. So notice at these pi over 4s, we have all of the same ordered pairs. I'm just remembering things I already know and pulling it together, that the signs of those points change. Now I've pulled my sixths in here to count by as well, but I'm actually going to drag that down so I have a little more space. So here I have my pi over sixths, and I'm going to think about counting these. I've got pi over 6, 2 pi over 6, which is pi over 3, 2 6 is 3, 3 pi over 6, which gives me pi over 2, 4 pi over 6, 4 6 is 2/3, so 2 pi over 3, 5 pi over 6 doesn't reduce, 6 pi over 6 is 1 pi, 7 pi over 6, 8 pi over 6, 8/6 reduced to 4 pi over 3. 9/6, 9/6 reduces to 3 pi over 2. And then we got 10 pi over 6, 5 pi over 3, 11 pi over 6, and then 12 pi over 6, 2 pi. All right, so we're just figuring out how we can develop these values. And so, as I've stated to you before, when I'm drawing my unit circle, I like to list my quadrantal and my pi over 4s first, and then I go in still counting the same way and I add these other values in. All right, so just to help us think, I'm going to go in here. I'm going to put my pi over 4. We said we listed those values. We made 3 ordered pairs. We've got 1, 2, 3, 1, 2, 3, and then we say 3, 2, 1. We take everything and divide it by 2. And then I put my square roots over all of my numbers in the numerator. Of course, I don't need to draw a square root over my 1 because the square root of 1 is 1. All right, so reflecting these, over here, I'm going to have negative x's. So I've got negative root 3 over 2, 1/2, and negative 1/2 root 3 over 2. All right, then we pull each of these down. We reflect them. And one thing I find is students take them and they just slide them down. We don't want to slide them. We want to think about folding them over that x-axis. So at 7 pi over 6, I actually have negative root 3 over 2, negative 1/2. And at 4 pi over 3, I have negative 1/2, negative root 3 over 2. So the points are the same. It's just that the y value became negated. And then lastly, we have 1/2 negative root 3 over 2. The x becomes positive as I shift them over to quadrant 4. And root 3 over 2, 1/2. All right, so all of this comes together, and I have kind of given you my idea, my method of how I build my magnificent unit circle, which you can now see right here. All right, so you want to be able to come up with these values. And again, I don't have this entire thing memorized. I have my pattern for making it memorized. I have quadrant 1 memorized, and then I can do a quick calculation in my head or a reflection to find any of these other points. All right, so I'm going to stop this video. In the next video, we're going to talk about using this unit circle to determine function values without a calculator.